All right. So we'll look at the first two here. And by the end of this, so it's going to be tough. Not at the beginning. It's okay if you look back to the answers after you do it to check. You know what I mean, as you're doing it. But let's just zip through one here. By the end, you should be able to look at one and go all the way through it and get it done. Okay. So the first one, it looks big and scary actually. Oh, I think I've made like 3 or 4 more videos here. Oh, maybe I'm just making 2. Oh no. I wonder where the other one went.
On the other page.
I know, but the time down here.
Yeah, there's like a different one for each page.
Is there?
Yeah.
Okay, cool. All right, that should be all right then. So let's look at this one. If we start our integral out here, okay, where am I starting? Where am I starting to measure the area of this thing? Nope. 2, right? This is A. Right? So it's like I'm starting, this is going to tell me the height of my rectangle, right? And so this little piece in here is the x that I'm plugging in. So that x is taking me here. Let's do it. So if this is the curve, and this is A to B, and inside of here somewhere I've got a rectangle. To this distance, I'm going to have A plus whatever a width is, right? So A plus whatever my first width is. So it's going to be from 2 to what up here? 5. Because the width of each rectangle is 3, right? Okay? So that's it. So I've got an f function. And the 3 over n is represented, what's the width in an integral? What looks like is missing from that integral right now? Dx. Dx is the infinitely thin width of each of my rectangles. Like once I cut it up like this little distance for that is going to be my infinitesimally thin width, right? Dx. That's it. Let's try 2. So this one's the limit. I'm going to look for a sum here. As n approaches infinity, for the sum as k is equal to 1, so I'm starting there, going out to n. Okay? And then I'm going to go f of, where am I starting? 1 plus k times 4 over n, all times 4 over n. Okay? Height, width. Okay, and it's almost like each of these you can kind of point to something, right? Like this integral sign is an adding machine. It sums them all, it sums everything up. The f of x is the height, and the dx is the width. Yep?
So Nancy, what is the point of rewriting the Riemann sum as a limit and the limit as a Riemann sum?
They just want you to understand the definition. Yeah, like this, but the idea is like that you're bringing up. It's like, what would you use this for? It's more like a theory question. It's like, what is an integral, right? So for these application problems, you won't see them. You won't see this skill used. Where you'll see this on when they do the assessments is either in the multiple choice, okay, or on like a 2 or 3 point free response where they're just asking you the exercise. They're just asking you to make the bridge between an integral and a sum. That's pretty much it. Let's see if this is actually working. Yeah, we're set. Okay, so let's make a little function here. And we'll call that function something really special, f of x. And make it look like that. And we want to find the area. First of all, we're going to estimate the area. And then second, we're going to find the exact area. But we're going to first try and estimate it over the interval from A to B in three separate rectangles. Okay, so that means I've got three bases here that we're going to set. All right, so here we go. In this first rectangle, let's find the base and the height of that rectangle. So can anybody tell me how far it is from here to here? From what we've got up there. That's it. That's good. Okay, that's what I want to hear. Okay, so down here, for my first width, or my first rectangle, right, I want a length and I want a width, and I'm going to put the width second. Okay, so I'm going to put b minus a over 3, because they're equal subdivisions. Okay, like all of these are the same. So I've got one rectangle there, I've got one over here. They're right-hand sums, right? And then I've got one over here. Okay, and we're going to call this one k is equal to 1. This one is going to be k is equal to 2, and this one's going to be k is equal to 3. Okay, so does that distance make sense? Does everybody see why this width? I've got a distance of b minus a there, and so if I just want this distance in here, it's going to be divided by 3, right? Because they're all the same amount of space for each rectangle, right? Each base is the same length. Okay, now if I want to go find how high this is right here, okay, I have to think about the function. So I've got to put an x into my function, right? So that distance x stretches from here to there. Okay, it's got two pieces. What's the first piece? 0 to a, or just a, right? Like I'm gonna plug in this x, right, into that spot, and that's gonna be a, and then I'm gonna add how much? B minus a over 3, right? It's gonna be this distance plus this distance. Is that okay? Yeah? Okay, so when I'm looking at these, this is the function, so I'm just putting this x, this distance, a plus b minus a over 3, into f of x, and it's giving me that height out, right? Does that make sense? So I've got the base times the height. This is the base times the height is giving me the area of that rectangle. Yeah? Sorry, thanks. Yeah. Yeah, you get the idea. Here, we'll do one of these. Okay, so let's do the second one now. Plus, okay, so this is going to be very similar, right? I'm going to get f of, well, here, let's do that part second. Okay, but my base is going to be the same here. Still the length of b minus a over 3. Right? And on the inside, now I'm going to here, right? Okay, so I want that a to start with. And then how many b minus a over 3s? I've put 2 in, right? Because I got one here and then another one here. That's going to get me this x. So when I put that into my function, it gets me that height. Right? That's an a, sorry, over 3. Everybody okay? All right. Now I think you get the idea. Okay. I wonder, probably not going to have enough space up there, so let's do this. Let's go and get an estimate of my integral of f of x, so dx, okay, with that Riemann sum. It's a right Riemann sum with 3 rectangles, okay? And let's just use summation notation to put them all down, okay? So that's the next little part of it, all right? So here's 1, here's 2. I don't think it's gonna, I don't have to go through how to get 3 as well, okay? But instead of writing that big, long mess down, okay, what a sum does is it gives you the instructions to do that by just writing it as one expression, okay? So my k is simply the rectangle that I'm going to start with. Like, which one am I going to start with? And on the top, goes, which rectangle am I going to finish my sum with, right? So it says I'm going to start with this one. I'm going to find that area, and I'm going to find all of the areas of the ones in between. In this case, there's only one. And then my last one that I'm going to find the area is 3. That's what this notation means, okay? I think everybody has seen that before, but I'm just kind of doing a refresher here, right?
So
All right.
K equals 1 beginning point, right?
It's the beginning rectangle. So k equals 1. The name of this rectangle is 1, right? So I'm starting at the first one, and then I'm gonna
How many rectangles are
yeah I'm gonna add up all the ones in between, and this is the one I'm gonna end at. Okay, so I need an expression that's similar to what we've got up here, but that's gonna work for every rectangle. Okay, so this first part, whoops, I'll get rid of that. Okay, there we go. Okay, this first part is just going to be f of, so I want same thing, I want a height times a width, right? So here's my height. This is going to be my width. Is the width ever going to change? No. So I can put b minus a over 3 there, right? Okay, and here, I'm just going to put in, this part's basically the same all the way through. Yeah, except instead of these constants here, okay, there's actually 1 out in front of this one, right? Okay, 1 is here, 2 is here. If I had another one out here, it would be 3. Okay, I'm just going to call that k times b minus a over 3, which makes good sense, because if I'm on the third rectangle, I need 3 of those widths to add to a to get to my x point, right? Is that all right?
Yeah.
Everybody okay? Okay, let's see if I can move this up here a little bit. There we go. Last but not least, let's actually do the integral. Okay, so if you could imagine, I just took it out of the way here. Sorry. Let's try this. Okay, if you could imagine now, what we're trying to get to is a spot where we can get the exact area under the curve. The way this one sits, okay, that's getting me underestimate here, overestimate here, overestimate here. It's a rough estimate at best, right? But if you could imagine an infinite amount of infinitely thin rectangles at every point that go through here, and I could add all of those up, that would get me the exact area under that curve, right? Does that make sense? So I'm going to have, and that's what we want to do, okay? So what's the kind of the tool that I'm going to use, the math tool that I'm going to use to add all of those things up? Right now, no calculus has happened, okay? What has to happen for some calculus to happen? You're saying integral, but we kind of talked about that here a little bit. Like, how do I, when I go in to define that integral, okay, how can I make, because it's kind of impossible, right? Like it's hard to conceptualize going through here and finding like an infinite amount of things to add up. Like, how can I add up an infinite amount of things and then get a number out of it? A limit, okay? We want to do that by way of a limit. So let's try that. So now our integral is going to go from a to b of f of x dx, and that's going to be exactly equal to the limit, okay? And now, as all of these amount of rectangles that I have, I'm going to have an infinite amount. We're going to call that n. As n approaches an infinitely big number, okay? And then we want to add them all up. So the sum, starting at k is equal to 1, all the way through the nth rectangle. Okay, here I gotta get this out of the way here. I wasn't getting rid of that. Sorry. Okay, through the nth rectangle, I should have put this down a little bit lower. But then it's the same on the inside, right? I still want to have a base, or sorry, height. But what's going to change now about the way I dictate that height?
N.
Underneath here,
N.
I'm going to have to divide by the number of rectangles, which is n, right? So that's what's approaching infinity, right? Times. So this is the height. And then b minus a over n is going to be the width. You guys all right with that? Okay. So here's my question. What's the difference between k and n?
K is the actual rectangle and N is the number of rectangles.
That's exactly right. Like this is n is the total. It's how many. If like I went through here and counted all of them, okay, or how many I put in there, it's the total amount of rectangles that are there. And in our case, that's an infinite amount. Okay, the k is the name of the specific rectangle that I'm looking at. All right, so if I'm looking at the 11th one, k is 11. All right, it's the name of that one that we're going at. So that's why that's a little bit different. Okay, you need both of those in there to complete the definition.
And if you're looking at like the infinite number of rectangles, so the nth one,
Mhm.
would you just replace k with n?
No, what you're doing, like the way the definition works, all right, is that we're substituting infinity into there as a limit, right? Like that's the reason we need to use a limit. I can't put infinity in and get a value out of it, right? But it's kind of a conceptual look at it. You know what I mean? So it allows us to do some math and get the value out. Okay? Okay. Let's go and try one of the questions they'll ask you to do. Killing me, man.